I'm using sample notation in most of these slides, but we can also talk about the same measures for the population. The difference is if the population itself is not small and data is not easily obtainable about it, we may not know the precise value for instance, the population mean. If I were to ask you about the average height of an American adult, it would be very hard to calculate that directly, simply because of how many there are and how hard it would be to collect all of that data. But on the other hand, I could collect a sample, and I could compute the average height in that sample, and I could do this process over and over and over again, and from the results I get from those samples, come up with a pretty good estimate of the population value. Okay? Still, we need to be able to talk about the distinction between those two things, and that's why we have different notation, and I will try to emphasize that in the discussion today. All right, so the first measure we will talk about is the mean. The mean of a set of data is what we usually think of as its average. And the way that is calculated is you add up all of the data values in your set and then divide by the number that are there. And so formulaically, this is how we would write it. This y bar, that's sample mean notation. What I'm doing there is I'm letting the y stand for individual values and the bar says for their average. Okay, so y bar is the sample mean. This is just conceptually what it means, is the total over the number. And by the way, I'll emphasize this now, in statistics, when we use the letter n, we are almost always talking about the sample size. So if you ever see n as a variable in statistics, assume sample size unless you're told otherwise. Does anyone know what this symbol is? It's in the numerator.
Oh, right.
I'm sorry, say it again?
Oh.
Okay, so it stands for the sum. What it actually is it's the capital Greek letter sigma. And the reason why it is the one that is used is it's the Greek equivalent of the letter S for sum. And a capital sigma almost always means add things up. Okay, now the notation looks a little different in different contexts, but in fact this is used in almost every math class from Algebra 2 on as a way to add up numbers in a particular sequence. So when we see this in statistics, we don't necessarily have a description here of the range of summation. Instead, we just say sum the y's. And you can think of that as add them all up. Okay. So this says add them all up and divide by n, and that will be our sample mean. Okay. So let's do a quick example. I have, what is this, 7 values? Yes, 7 values. What's the sample mean here?
So is it 60 divided by 7?
What I get? You want to know what that is? We do have calculators for this, but I can't resist. I'm a number theorist. I have to show you this. So 60 divided by 7, I guess it would be 8.571428. So how do I know that? Well, it's 8 and 4/7. And there's this really neat thing about the way sevenths work. So 1/7 is 0.142857, repeating. So that just repeats indefinitely. 2/7 also repeats indefinitely. Notice anything?
It doubles.
It did double. That's what we'd expect, right?
Yeah.
But even more, 142857, this is the same sequence in the same order, but just at a different starting point. That's really kind of unusual. And that pattern continues This is what makes sevenths so interesting. Let's see, 4, 2, 8, 5, 7, 1. 4, 2, 8, 5, 7, 1. Again, same sequence, same order, different starting point. And since I've already done this, why not just do the rest? Let's see, this would be 5, 7, 1, 4, 2, 8. Repeating. This one I think is 7, 1, 4, 2, 8. Six sevenths is 8, 5, 1, 4, 2. Oh, 8, 5, 7, excuse me. 4, 2. And of course, 7 sevenths is 1. Kind of an interesting feature of sevenths. So if you ever have to do a quick calculation with sevenths, actually all you have to memorize is this first one. And then it's just about getting the right starting point, which you can actually pretty much estimate. 3 sevenths is just less than a half. So that's why I started with 0.4. And if I know the sequence, everything else comes from that. Just an interesting feature. Not terribly important to statistics, but still, I'm not a theorist, so I have to take those chances. So, all right. Back to where we were. So we said 60 sevenths. 60 sevenths, which is 8 and 4 sevenths. Or, yes, 8 and 4 sevenths, so 8.571428. Okay. So that's the basic idea for calculating the mean. Hopefully you've had plenty of practice with this before. We will do some more in just a few minutes, and I'll show you how to use Excel to do this quickly, especially when you have a large number of data values. Okay, the median. You may have heard this before as well with a finite set of data. The way we calculate the median is we look for the middle value if we were to list the values in order. Okay? Now, in a histogram, you can find the median value as the one location that splits the area underneath the histogram bars in half, where half of it is to the left and half of it is to the right. So when I look at that same data we had before on the earthquakes that caused tsunamis, the median here is about 7.5. And that's because if I take all of the area under the bars from 7.5 and below, and all the areas under the bars from 7.5 and above, those two areas are approximately equal. And that is the place that makes that as close to equal as possible. So that would be the median value. We'll have a more formal term for this later on when we talk about percentiles. So let's, again, do this with specific examples to make sure we're in the same line of thinking. I have a set here with how many elements? 1, 2, 3, 4, 5, 6, 7. Where would I find the median for this set of 7 elements?
In the middle.
Okay, so what number in particular would it be here?
6.
Good. What I can do is if it's small enough here, I can probably just see that 6 is the middle element. But if it's large enough, or if I'm tired or whatever, I can balance things by eliminating endpoints. I can get the 1 and the 13 paired off, the 3 and the 11, the 5 and the 8, and then the 6 is the lone element here in the middle. So that means 6 is my median because exactly half the numbers are below it and half the numbers are above it. Okay. All right, what about this one? 2 other things are happening here. First, how many elements does it have?
6.
6. So that's a different number, so we'll have to think carefully about how that works. And second, the first set was nicely organized for us. It was organized from smallest to largest. That made it very easy to find the middle value by literally looking for the middle of the set itself. In this case, the set is not pre-ordered. So because of that, I cannot simply look at the structure of the set and know where the median is. I have to actually reorder it, either from least to greatest or from greatest to least. I usually default to least to greatest, and then find the midpoint. So let's do that first part. If I reorder this set from least to greatest, it would read 5, 7, 11, 12, 12, and 13. Okay. Well then, how do I find the midpoint when there are 6 elements? I should go ahead and write that in here. So just reordering this, we have 5, 7, 11, 12, 12, and 13.
Would you take the 2 middle numbers and divide by 2?
Okay, good. So when I'm looking for a midpoint, I can try to follow that same approach. I can eliminate the first and the last, that's 5 and 13, the 7 and the 12, and then I'm left with these 2 numbers here, this 11 and this 12. So clearly the median has to be somewhere between them. And statisticians, mathematicians, whichever you prefer, when you're trying to decide where between 2 numbers to pick the midpoint, we usually just average them and go exactly halfway between those 2. So exactly halfway between 11 and 12 is what happens when you take 11 plus 12 and divide it by 2. That would be 11.5, and that is the median here. So the median is 11.5 in this instance. All right, so just to summarize what we just did, when you're finding the median, if you have a finite set, the easiest thing to do is to list it out in order. If you have a small set, I should say, is to list it out in order and then look for the middle value. If you have an odd number for your sample size, an odd number of n, then the midpoint will be one of your data values, and that will be the median. It will be the very middle one in your list. On the other hand, if you have an even number in your set, so your n value here is even, then you'll actually have to split halfway between the 2 numbers that are on either side of that midpoint. And the way we do that is we average those 2 middle numbers. No problem. Thanks for letting me know. Have you on the attendance? Yes, that's good to know. Okay. Let me check. You want to put it here today. By the way, this is a good time to mention, so at the end of the day, I embed the quiz, I post the video, and I update the attendance. If you find that you were here during class time, but the attendance doesn't reflect that, please just send me an email. I can always, of course, go back and verify, but I'd rather you tell me that your attendance is inaccurate, and I can then correct that on the record. All right, so we've talked about mean, we talked about median. What's the difference in terms of what they tell us? So before I go too far, I do want to say those are both measures of what we call the center of our data. So it's kind of hard to define explicitly, but think of the center as what would we say is the middle or a typical value. Okay? And we can think of that typical value in lots of different ways. That's why we have different possible measures for it. But each has advantages and disadvantages. So this question is intended to get you to think about what the advantages of one versus the other might be. So suppose, for whatever reason, we're doing a study of heights of statistics students, and we measure the height of 9 students in the class. If we find that the median is larger than the mean, what does that tell us about this group?
Is it just that sample is unusually taller? Or
Could be. Depending on what you mean by that.
You could have some pretty significant outliers.
We could. So let's think about this. If I have 9 students, okay. If I have 9 students, and the median is larger than the mean. That's what we said, right? Down. or not. There we go. So suppose these are my 9 people. Well, which one is the median if they're listed in order here?
E.
Right. The 5th element out of the 9 would be the median. This is my median. Okay. I'll just go ahead and replace that in so we can see it. If the median is bigger than the mean, then that means when I add up all these numbers and average them, the average is somewhere in this direction. What could cause that? There's a few different ways it could. Go ahead.
Is that what the skew would be on the chart?
That would be one way that might show up, right? If I had a particularly short person included in the sample here, that would pull my average down a good bit, right? And then maybe the people who are taller than the median are only just a little bit taller than the median. So in that case, what I would find is the median is still right here in the middle, but that particularly short person pulls the average down and therefore makes the mean smaller than the median or the median bigger than the mean. Okay? Not always immediate just from seeing that information, but when you think about it, you can kind of see at least one way that that could play out. So this is really kind of an important idea. And one of the examples I like to use is if you think about if you have a focus group who's trying to study something, and perhaps you're studying shopping habits, and in your focus group you have 15 people, and one of those people just happened to be, I don't know, let's pick a person, Elon Musk. The average income in your group is likely to have a median that is below the mean. And the reason is because there's one person who is greatly skewing that. And so what I'm trying to emphasize there is one of the problems with the mean is that it's very sensitive to extreme values. If I have an extremely large and extremely small value, the mean can be pulled pretty far by that one value. On the other hand, the median is not quite so sensitive. Okay? So let's talk through what that means. So suppose we've done this. We've got our group of 9, and we know that the median is a little bit bigger than the mean. Okay? Suppose we take that group and we add the shortest person in the whole class to it. So now we have 10 people in the group, and what we've done is we've added a person on the short end. What will that do to those two measures? What will it do to the mean? Just generally. Bigger, smaller, the same.
Reduce it, yeah.
Yeah, I mean, you're adding the smallest person, so they're going to be smaller than every other value that was in there. So it's going to pull the value down. So the mean will go down. And probably by a moderate amount, right? Because it's smaller than every other value, so it probably will pull it down a good bit, especially if we already had an extreme value that was pulling the mean down. What about the median? Will the median be larger, smaller, or the same?
The same.
Close. Close. It won't be the same. What will happen is if we take that list from A through I, we basically added another person in front of A. So now instead of our median being the eth person, it'll be halfway between D and E. So it will move left or down by half a step, which may or may not change the value. If those two values are the same, it actually will be the same median in that sense. But it's only ever so slightly smaller. Okay? And again, that's one difference between the mean and the median. If you add in an extreme value, the mean can be affected pretty significantly unless you have a huge data set. The median, on the other hand, is likely to only be affected by a small amount. Different advantages and disadvantages to both of those approaches. All right, questions about that? Okay. All right, well, let's turn our attention then away from the center and instead towards spread. So when we talk about a data set or a variables distribution, we will want to know where is its center, and then how is it spread out around that center. Those two pieces of information give us a picture for roughly what the data set looks like. So one measure, a simple measure, is what's called the range. And when we have a collection of data values, we can compute the range by simply taking the difference between the largest value and the smallest value. It tells us how wide the entire set of data actually happens to be. So using that same data set that I had before, where the smallest value here is 3 and the largest is, 18, what's the range?
15.
Yeah, just take the 18 minus 3, and it's 15. And of course, I want to emphasize, avoid the mistake of assuming this is the smallest and this is the largest just because of the first and the last in the set. There's no reason why when you collect the data, it has to come in order. So that's the range. Okay, so is the range sensitive to extreme values? Yeah, definitely. If I throw in the smallest person, it's going to change my range. And depending on how much smaller, then it's going to change it a lot. Okay, so it is very sensitive to extreme values. Okay, so another measure of spread that you've probably seen before is what's called standard deviation. Now, standard deviation is really defined first by looking at what's called variance, and then the standard deviation is just the square root of that. And there's also a different notion for standard deviation in a sample as opposed to in a population. So I'm going to start with the sample standard deviation, and I will show you how to calculate that manually and then also how to calculate it within Excel. Okay. So first, the variance. Nice, nice. So the variance of a data set is the sum of the squared deviations divided by n minus 1. Okay, again, n here is, as always in statistics, the number of values that we're looking at, the number in our set, the size of the sample. So let me unpack the other pieces of that definition. Hopefully we all know what the sum is. The squared deviations. Well, let's start with deviations. Essentially, when we're trying to measure spread, what we, at least with variance and standard deviation, we're comparing individual values to the average value, to the mean. And so when we talk about the deviations, we're asking how far from the mean was that particular value. Okay? And so here in my notation, my summation notation here, I have y minus y bar, and what I'm doing is for every single value in my set, I'm computing the difference between that particular value and the average for the set. In each case, the difference that I compute is called the deviation for that value. Then I square those things. And what that does is it eliminates negative signs, for instance, and it also tends to more strongly weight values that are farther away. Finally, I add up all of the resulting squared deviations, and then I'm almost averaging that, but instead what I'm doing is I'm dividing by n minus 1. Okay, now there's a reason for that. It's somewhat complicated. I'm not going to talk about it in this class, but it comes from the fact that we are estimating the mean to subtract here using the sample mean. Our sample mean doesn't have to be the same as the population mean, and because of that, because we have to use the sample mean, we have to use an n minus 1 here. When we do that, the result, we call it s squared, and that's called the sample variance. When we want the sample standard deviation, we simply want the s, and we take the square root of both sides here, and that will give us the sample standard deviation. Okay. So that's a lot of pieces. What I'm going to do is I'm going to shift gears right now and move towards Excel, and I'm going to have you give me a data set. We will compute manually, one step at a time, the sample standard deviation, and then I'll show you a single command that does all of that for you in Excel. And that way you can see both sides of it. There's at least one homework question that asks you to fill out the chart that you would use to compute this manually, and the main reason is just I want you to understand how it's calculated. But thereafter, you can use a computer or a calculator to compute the standard deviation whenever you need. I won't expect you to do it every single time. I just want you to do it at least once so you know how it's done. All right, so let's do that. I would like you to give me a set of 6 numbers. We will calculate its mean, its variance, and its standard deviation, at least in the sample form. Let me switch over to Excel. All right. So, I'll call them y values. And then, yeah, give me 6 values.
Okay.
I'm going to say 6.
66.
Okay.
7.
7.
20.
20.
Yeah, 20.
Okay.
13.
13. One more.
10.
10. All right, let's see. Now, computing the average, 13 plus 7 is 20, plus 30 is 50, plus 72 is 122. Okay, so it's 122 over 6. And there we go, 20 and a third, 20.3 is my average value. Okay. Now there's a way to do that with a single command. And what you do is you type in equals AV. You'll notice that average is one of my options. When I click on it, double click on it, excuse me, it asks me what are my inputs, and I can highlight the 6 values. And there we go. It computed it manually for me, found the same value, so it looks like it did the work correctly. Okay. So, yeah, I'm going to put a row here. I get what these things are. I want to compute the deviation, the square deviation, and then add those up. Okay. So let's see, y minus the mean. What I'm going to do is I'm going to take 6 and subtract 20.33. That'd be negative 14.33. What I will do is I'll actually take this value minus this value. And there it is. Back, since I want that to stay the same, let's go to this formula. If you know how to do this, this is great. If you don't, that's okay. This is how it's done. And there we go. Good. When I do that and I click and drag from the bottom right corner down, it uses the same formula, but it advances the input point 1 each time. So this time it's using this value, the next time it's using this value, the time after that it's using this value. When I put the dollar sign inside the C12, what it's doing is it's fixing that 12. It's not going to increment the 12 each time as well. It's going to stay with that same average that it subtracts. And so this is actually the deviation I'd expect each time. We can check it. The average was 20.33. If I take 10 minus that, I'll get negative 10.333. So sure enough, that is the deviation. Now, for the square deviation, all I want to do is to take the deviation I just found and square it. So I want to take this number and multiply it by itself. And there we go. So when I do that for each of them, I can click on this bottom right-hand corner, drag down, and there's each of those squared deviations. Now, I'm going to essentially compute an average of these in just a moment. It's not exactly that, but it's close. And you can see, how do they contribute? Well, the ones that are close to 20.33, like this 20, they don't contribute a lot at all. This is 1/9. That's a very, very small amount. This one, on the other hand, is pretty far away. It contributes 2,085 to that total of squared deviations. So it's taking those extreme values and it's giving them a lot of weight in that sense. And the last thing I want to do is add up these things and then divide by n minus 1. So to add them up, I'm taking the sum, double click that, ask for the inputs, and there they are. There's my total squared deviations. That's the numerator of my variance formula. Write that formula down here. S squared equals sum of the squared deviations divided by n minus 1. Alright, so here's my sum of squared deviations. That's the entire numerator there. And then my sample variance is going to be that number divided by n minus 1, which I guess I chose 6 values. So I divide by 5. So that's my sample variance. And here's my sample standard deviation. SQRT for square root of that value. So it looks like my sample standard deviation is 22.93. Okay, that's a lot of work. One of the homework questions will ask you to essentially fill out this table. They'll give you these values, and they'll ask you to compute the deviation. You just take the value itself, subtract the mean. The square deviation, you square the thing you just got. The total square deviation, you just add those things together. And then the variance, you divide that result by n minus 1, if it's a sample. Okay. Now, a moment of truth, did I do this correctly? Excel has a function that computes the sample standard deviation. If you type in equals, it tells it you're going to type in a formula. I'm going to type in ST for standard deviation. You notice there's a lot of things here. I'm going to choose STDEV.S. That means sample standard deviation. The .P would be a population standard deviation. We'll talk about that in just a moment. Click on that. I want to compute the sample standard deviation of these numbers. And there it is. It's the same value we just computed manually, but Excel does it in one step for us, which is great. I believe exactly the same notation for every piece that I just did there will also apply to Google Sheets and any other spreadsheet program you like to use. If you use OpenOffice or I forget the one that Apple has. Blanking on the name, sorry, but all of them have features of the same sort, and I believe they all use essentially the same notation for it. So that should be a pretty easy way to do that. Okay. Questions on that example? And hopefully it's clear. I let you choose any of the 6 values you wanted. We even chose some pretty extreme values here in this case compared to the rest. And you can see that the way we calculated this manually lines up with the correct formal value. All right. Well, stay away from that for a moment. Go back to the slides. Okay, so we did that. We computed this sample variance, and when we took the square root, we got the sample standard deviation. In that case, it was 22.93 approximately. That gives us a measure for how spread out the data set might be. I want to emphasize the difference between the sample standard deviation and the population standard deviation. The symbol we use for a population standard deviation, or for a population variance in this case, is lowercase sigma. Right? Again, it's the Greek s, but it's a lowercase to parallel with the lowercase s for samples. If you ever see a sigma in a statistics class, it stands for standard deviation of the population. It's always a population value, so remember population when you see that. This formula gives me the population variance. That's the sigma squared value. I add up the squared deviations. Actually, here it should be a mu, not a y bar. I apologize for that. I'll fix that in the slide before I post them. You want to take the individual values in the population and subtract the population mean. So this is not correct. This should not be a sample mean. This is a population mean. Square those deviations, add them up, and here's the one difference in the formula. I divide by n, where n is the number of members of my population. I can do this when I have all the population in my set. Okay? And if I want to do that in Excel, I can use that same calculation thing. I type in equals st, should give me the standard deviation as one of the options. You want stdev.p for population. And that's what you're looking for when you're looking for sigma. How are they different? Well, honestly, let's do this. If I, instead of dividing by n minus 1, if I divide it by n, what it will actually do is it will make my value just a bit smaller. So the population standard deviation is always going to be a little bit smaller than the sample standard deviation. So suppose I decided that this was my entire population. If so, then this average is a population average, which we call mu, the Greek letter mu. We'll see this later in the discussion. I did use it in other notational places. If I want the population standard deviation, I type in ST for standard deviation. This is the one I select. I'll have it compute them. And you can see it's very close, but it's a little smaller. Again, I'm dividing by n as opposed to dividing by n minus 1. And then when I take the square root afterwards, I get the population standard deviation. Okay. Any questions about that? So that's computing standard deviation. Again, most of the time we'll use technologies to do those computations for us. But at least once on the homework, I do want you to go through one example where you compute it manually so you can see how it works and understand how individual values contribute to that total. But in practice, this is the way most of it will be done. When I took statistics, we did have calculators available to us, but they were mostly handheld calculators. And we did have powerful computer programs that could do things, but the class was taught around memorize these formulas and know how to use them. And that was painful. But it can be done. I want you to do it once, and thereafter I'll call it good. So I'm trying to get back the slides. There we go. All right, any questions about that? Okay. So there are other measures of spread as well, besides just the variance and the standard deviation, which are interconnected. We can talk about quartiles, and we can also talk about percentiles. So probably the best thing to remember there is just look at the base word, the root. Quartiles, quart comes from four. Watch for in Latin. Quartiles are splitting it into 4 groups, and each quartile is the boundary point for that particular group. So the first quartile is the boundary point for the lower 25%. The second quartile would be the boundary point for the lower 50%. The third quartile would be the boundary point for the lower 75% or the upper 25%. And then, of course, the last quartile would be the 100th percentile. Okay, so for any percentage that I want to choose, I'm not limited just to the 25, 50, and 75. I could look at any percentage and then consider what's called a percentile, which is the particular data value below which you'll find that percent of all values. So just as a simple example, thinking about percentiles, the median, if you'll recall, is the value below which you find half the values and above which you find half the values. So it's the midpoint in that ordered sense. What percentile does that correspond to?
50.
Yeah, the 50th percentile. We expect 50% to be below it and 50% to be above it. And if you've ever taken a standardized test, sometimes they will report a percentile for your score. Anyone know what the highest percentile there is? So you may or may not have seen this, but the highest percentile that can be reported in those situations is the 99th percentile. And the reason is because when they report that your percentile is the 99th percentile, then they're saying that your score was better than 99% of the other participants on the test. And it is not possible for your score to be better than 100% of the participants on the test because, for instance, your score is in that set. You can't be better than your own score. So that's why the 99th is often the highest when they list a percentile on a performance. All right. Another measure of spread that's related to this is called the interquartile range. So remember, the range from a few moments ago is the width of the entire data set. It's the difference between the largest value and the smallest value in the whole set. Okay. The interquartile range is actually the range between what's called the lower quartile and the upper quartile. Let me back up. I think I forgot to emphasize those in my last slide. The lower quartile is what we call the 25th percentile. It is the boundary point for the lower 25%. The upper quartile is also known as the 75th percentile, and so we would say it bounds the upper 25th percent. Okay, so when we talk about the quartiles, we're basically looking at the boundaries between splitting the data into 4 equally sized groups. Okay? The lower quartile is here between the bottom 25% and the next 25%. The median is between the second 25% and the third 25%. And then the upper quartile, or third quartile, is between the third 25% and the upper 25%. So when I talk about the interquartile range, what I'm doing is I'm taking this boundary point and finding what's the width there between those two. So let's do that for this particular set. I'm going to try to write this on the screen. So I want to compute the interquartile range for the same set we've been working with thus far. And it's going to help me, first of all, to figure out where are those quartiles. I can do that if I write them out in order. So let's reorder this set from least to greatest. All right, smallest one is a 3. And then there's 2 5s, and a 6, and a 10, and a 13, and an 18. Did I get everything? Yes. Okay. Now, if I want to find the lower quartile, probably the best thing to think about is it's the 25th percentile. So what I can do is I can take my whole data set, find the median, and then focus on just the lower half. That'd be the lower 50%. The median of the lower 50% would be my lower quartile. Right? It's the midpoint of 0 to 50. That's going to be the 25. So let's see. Where was my median for this set?
6.
Right here at 6. So what I'm going to do is I'm going to ignore the 6 and focus just on the 3, 5, and 5. What's the median of that set?
5.
5. So we would say the first quartile is 5. Okay. What about the third quartile? We're going to find the third quartile, do the same thing. I take this median here, at 6, and I look only at the parts above it. That'd be the upper 50%. The median of that set is the 75th percentile, or the third quartile.
13.
So when I look at these three, the number right in the middle is 13. All I need to do to compute the IQR is to take the difference, Q3 minus Q1, which in this case is 13 minus 5. So the interquartile range is 8. All right. So, any questions about how that's computed? Okay. Another important thing to recognize is just like happened with the mean and the median, these measures of spread have different sensitivity levels to extreme values. We saw in our calculation on Excel that one large value that was far away from the mean contributed a lot to the calculation of that standard deviation. Right? That single value that was 45 away, had a deviation of 45, was a huge contributor to that total. I think of the 23 or so that we found for the sample standard deviation, essentially 20 of it came from that. That's a lot. On the other hand, IQR is not quite as sensitive to it. If I have one extreme value, what it does is it shifts everything a half step. And so it will shift both the Q3 and the Q1 a half step in the direction of that, I guess it'd be a quarter step for those, but in the direction of that extreme value. And so it can change the IQR, but it is unlikely for it to change it by a lot if there's just a single large value that's been added in either direction. Okay. So there are different types of distributions where the mean and the standard deviation might be useful to use versus where the median and the IQR might be useful to use. But we actually tend to pair them in that way. We'll talk about this in just a few minutes. We tend to pair the mean with the standard deviation and the median with the IQR because of their respective sensitivities to those extreme values. And then we decide which to use by looking at our particular distribution and asking which measure would be more appropriate based on whether we see a lot of extreme values or not. All right, so I'm going to do one more thing, and then we'll take a brief break before we talk about the last portion of the discussion. So another thing that is often used in describing a data set is a 5-number summary. And a 5-number summary, as the name implies, is a list of 5 numbers describing the set. And those 5 numbers are all related to particular benchmarks in an ordered list of the set. So what we do is we give 5 different pieces. Let me actually just write these out on the slides. The 5 numbers are the minimum, the first quartile, the median, the third quartile, and the maximum. All right, so you can kind of think of it as, it's not exactly, but essentially the 0th percentile, 25th, 50th, 75th, and again, not exactly, but essentially 100th percentile. When you look at it that way, it does give you a sense of how the data is spread around. You can find 25% of the values in between any pair of them. And so it gives you nice benchmarks for how the data progresses. So let's give the 5-number summary for this same set we've been working with. Let's see if I can remember. All right, so what is my first element here in the 5-number summary? 3. Good. That's my minimum. What is the next number? First quartile. We found that a minute ago. Does anyone remember?
5.
Yeah, we found that was 5. What was the median?
6.
6.
What was the third quartile? 13, I think.
13.
Good. And then the maximum is, of course, 18. So those are my 5 numbers, and sometimes we'll write it with a dash in between. I've seen both notations. What matters to me is less that part of the notation and more that you know which numbers go where. Okay. You can essentially think about this as giving you benchmarks for how to progress through the data 25% at a time. Okay. You start at the 3, the next 25% happen between the 3 and the 5, the next 25% happen between 5 and 6, the next 25% are between 6 and 13, and the last 25% are between 13 and 18. So it quickly, in just listing 5 numbers, gives you a nice picture of what the set looks like. Just double checking that that's, yep, we'll start with box plots next. So on my clock, it is 10:24. Let's make it a 6-minute break just so things are even, and we'll start at 10:30. So I will see you in about 6 minutes, and we'll start with box plots. Okay. So we talked about 5 number summaries. Let's talk now about a visualization of those 5 number summaries called a box plot. So a box plot is a way to essentially graphically show what that 5 number summary looks like. And in fact, we can do a little bit more than that because we can actually see values that are relatively extreme, values that we would call, the term we use is outliers. Okay? Now, box plots are sometimes horizontal, sometimes vertical. The idea is exactly the same in either case. I chose to use vertical here simply because it fit well with the slides that I had produced. It's easier to see it when it's side by side in that way. But I don't even recall if the box plots in my math are horizontal or vertical. But you can tell it's exactly the same thing. Rather than using a vertical axis, I'll use a horizontal axis, and my box plot will be sideways rather than vertical. Everything else is exactly the same, so it should not matter in that sense. So how do we build a box plot? Well, the first thing we need to do is we need to know those points that are going to be relevant to it. So we need to know the numbers involved in the 5 number summary. Okay, remember those 5 numbers are the minimum, the first quartile, the median, the third quartile, and the maximum. And always in that order. So the first thing we do is we draw the axis that we're going to use to represent the numerical values in our data set. And so we essentially need to cover the entire range that the data set represents, everything from the minimum to the maximum value. This is built using that same data on earthquakes that caused tsunamis about which we have data. And if we looked at the 5 number summary there, we can find the first quartile, the median, and the third quartile, and use those to build the first piece of our box plot. So what we do is we draw that vertical axis, spanning the place where we see values. If you'll recall from the histogram, those values were all between 3 and 9.5. And we draw short, in this case horizontal lines, at the lower and upper quartiles and the median. So that's a line right here, a line right here at the median, and a line right here at the first quartile. If it's a horizontal box plot, those will be vertical lines, but again at the same points. Okay. We then connect each of those 3 lines on the outer sides, and the result is a box from which we get the name box plot. And that box is essentially a rectangle that contains everything between the first quartile and the third quartile, with a line in the middle marking where the median might be. Okay? And you can kind of see that this box is not necessarily symmetric. The median doesn't have to be exactly halfway between the first quartile and the third quartile. So we can kind of see there's more values compressed in this upper portion than there are in this lower portion. Okay? That's one of the things that the box plot helps us visualize. At that point, we've built our box. We then need to build the stems. Well, we'll start with the fences first. That tells us the boundaries for those. So the first thing we'll do then to decide where these fences are located is we compute the interquartile range. Now, the interquartile range is the distance between the first quartile and the third quartile. In terms of the box, it's essentially going to be the height for a vertical box or the width for a horizontal box. It's the difference between this point and this point, the first quartile and the third quartile. That's the IQR, and we essentially allow ourselves some wiggle room 1.5 times the IQR, either above the third quartile or below the first quartile. So let's see, just estimating here, my interquartile range looks to be about 1, right, from about 6.7-ish to about 7.7-ish. So I think my interquartile range there is 1. 1.5 times that would be 1.5. And so what I do is I add 1.5 on top of the 7.7. It's not quite that, I guess. It's close. But if I add that on top, that would be where my upper fence is located. If I subtract that from the first quartile, so take this number minus the 1.5 or whatever it might be, that gives me my lower fence. So temporarily, I will draw in a dashed line where those fences are located. The reason is because it helps me visualize what's happening, but in the actual box plot itself, those fences don't have to be drawn in. Okay, they're essentially boundaries, but they can be invisible boundaries. That's okay. I draw them in when I'm doing it manually to remind myself, but if you use a computer program, for instance, to draw them, it usually will not draw in those fences, and that's okay. All right, any questions so far about what we've done? Once you know the 5-number summary, it's not hard to produce the box. You can compute the IQR just by subtracting the second and fourth numbers in that 5-number summary list. 1.5 times that is what you add to the upper quartile and subtract from the lower quartile to find where the fences are located. Okay. So then we draw, I guess whiskers is the term that we're using here. We draw whiskers from those box plots. We start at, in this case, the upper quartile, Q3, and we extend that whisker inside the fences as far as we can go to the largest data point that's inside those fences. Okay, so the largest value that's inside the fences here looks like it's about 8.8-ish. That's the end point of that fence, and so we draw the end of that whisker there. Similarly, on the lower side, we extend the whisker from the first quartile down, and we go as far inside the fences as we can to the smallest data point that is within the fences. That's the majority of the structure of my box plot. If there's a data value outside the fences, we don't connect it with the whisker. Instead, those outside the fences values are drawn in separately. Okay? So this is a way of emphasizing what we will often consider to be an outlier. It's not a guarantee. There's actually some discussion required, some consideration required to decide whether a data point is an outlier or not. But one good rule of thumb is if you use that 1.5 IQR away from the respective quartiles, the value that falls outside the resulting fences is often called an outlier because that's a good rule of thumb for deciding that. It looks like in this case we had 6 total outliers, 2 that were above the upper fence, and 4 that were below the lower fence. Any questions about that so far? So that's the main idea for box plots. Now, 2 additional things that are in this chapter, they will come up in the homework, but they will also be things that we will use in chapters 3 and 4 and 5. So it'll be really important to nail this down now. Is first, standardizing comparisons using the mean and the standard deviation. And the second is the empirical rules we'll talk about in just a moment. So let's start with standardizing values. When would you want to do this? Well, so I'm a sports fan. One of the most common things that comes up is which player was the best player of all time, or which team was the best team of all time. And the common thread in most of those discussions is it's really hard to do this because they're in different eras. They play different games, and so you're comparing apples and oranges. It's really hard to do that. Well, the purpose of comparing using the mean and the standard deviation with the standardization is what we're doing is we're finding a way to take apples and oranges as a discussion and convert them both to the same thing so that we can then actually compare them. And we can actually ask which value was more unique. That is, which player was more unique in their time frame. That would be one way of measuring which one was the more significant and perhaps because of that greatest player of all time. Okay, so one of the common things to ask is, I think there's the Seattle Mariners in one of the early 2000 years had an extraordinarily large number of wins in their regular season. And I think it's still a record for the most wins in the MLB. A few years before that, the Chicago Bulls had 72 wins, I think it was. And that was, at the time, considered almost unbreakable. 72 wins out of an 82-game season. I know that later the Warriors had 73 wins. So, which of those accomplishments is more significant? 73 wins in an NBA season, or I forget how many it was that the Mariners had in an MLB season. The Mariners had a lower percentage of wins, but it's a little harder to have a high number or a high percentage of wins in the major leagues than it is in the NBA. The gap between the really good and really bad teams is not quite the same. There's also a little bit more of a parity, I guess you'd say. Really good teams might win 60, 65% of the time, versus in the NBA, really good teams should be winning more like 75, 80% of the time. So how do you compare those things? Well, we can use this idea of standardization to decide which is more unusual given the distribution it lives in. So here's how we do it. We compute what's called a z-score. There should be a hyphen there. I can fix that later too. And the way we compute a z-score is and I'm going to describe this in words because this will come up a lot. We compute the observed minus the expected over the standard deviation. Okay? We'll be doing an equivalent of this in a lot of contexts throughout the course. So if you get used to this mantra, observed minus expected over the standard deviation, it'll help you a lot. So depending on whether we're looking at a population or a sample, the way that might look is if I were to decide what would be expected, if I'm just randomly guessing a particular value, my best guess is probably going to be the average, right? The average is a good measure for the center. If I don't know what value to guess, I'm going to guess the average value right there. And so the average in the population is this symbol mu, and in a sample, it's the symbol x bar. Okay. The standard deviation in a population is sigma, and the standard deviation in a sample is s, and then this x is just an individual value that we're computing this for. When you do this, what you're actually calculating is how many standard deviations above or below the mean does your particular data value live? How far away from the mean in terms of the number of standard deviations is it? One way that I've heard this expressed is we're using the mean as our center point, and then the standard deviation as our measuring stick, as our ruler, for deciding how far from the mean was that particular value. This puts everything on a similar scale, and so things that are more standard deviations away are more unusual. And if they're more away in a positive direction, then they're much higher than usual. If they're more away in the negative direction, so a more negative z-score would mean it's significantly lower than usual. And you can also tell, observed minus expected, if that value is positive, any positive z-score is above the mean. Any negative z-score is below the mean. And then a z-score of 0 is one that fell right at the mean. So let's do a quick example just to see how that plays out. So suppose, this example I got from our book, suppose I have two students, John and Ali, who are from different high schools. and they're arguing about who's the better student, which one has the highest GPA compared to their school. And unfortunately, like many high schools, they have different ways of measuring this. One high school does it on the standard 4.0 scale, and another does it on the 100-point scale. So how do we decide which one of these is more unusual? And of course, there's different distributions at each school as well. So here's how we could do it. We could look at the mean for each individual school and call that an expected value. We can look at the actual GPA for each of these two students and call that the observed value, and then use the standard deviation for each school as our ruler to decide how far from the mean was that one student. Okay. So let's compute this. Do it first with annotation, and then we'll see it on the screen as well. So if I want to compute the z-score for John, what I do, call it this, z for John, is the observed minus the expected over the standard deviation. I always write that down or say it aloud in my head so I can remind myself what goes where. And again, you'll see this coming up in a lot of different contexts, so it's helpful to think of it as observed minus expected over whatever the equivalent of standard deviation is in your case. So what did we observe for John? Well, we observed his GPA as a 2.85. And if we were just picking a random student from his school, what would we expect on average? Well, we'd expect the average 3.0. So that's his deviation from the average. And if I divide that by the standard deviation, which is 0.7, that will give me a metric for how many standard deviations away from the mean was John's GPA. Okay, so let's see, that is negative 0.15 over 0.7. Which is going to be 2 and, excuse me, 0.2 and 1/70th. Going to round to 0.21. And with a negative sign because it's below the average. So he is a little bit more than 1/5 of a standard deviation below the mean at his school. Okay. That tells us where in the distribution that his value fell. Now let's think about Ali. Again, I'm going to remind myself I'm calculating the observed minus the expected over the standard deviation. The observed for Ali was a 77 as his GPA. Again, this is on a different scale, so the value of the standardization, we can see how many standard deviations above or below he fell, and decide from that which one did better compared to their peers. So his observed was 77. If I were picking a random student at his school, that would be 80. And the standard deviation at his school is 10 points. All right, so what does that amount to? Negative 3 over 10, which is negative 0.3. I'll go ahead and put an extra 0 so I can compare them. All right, so whose z-score was higher? Be careful here because they're both negative.
John?
Right. John's z-score was higher. One way of looking at that is it was less negative. So he was closer to the mean. They were both below the mean, but he was closer to the mean than Ali. So it looks like he did better. Okay? And so, again, we took wildly different scales here, and we were able to convert them to a standardized scale so that we can then compare them directly. If I wanted to win that sports argument with someone who was okay with me pulling those kinds of statistics, I could compare the z-score for the Seattle Mariners with the z-score for the Golden State Warriors and decide which z-score is higher. And that might be one way to decide this team was more significant, was definitely a better team compared to all the teams that they played against than the other, even though they play different sports in different leagues. Okay. Questions about that? By the way, I mentioned that I'm into chess. I should mention that there's a metric used for rating chess players. When you ever find a chess player's rating, it's on a scale essentially from 0 to 3,000. It isn't limited to that, but because of the way that the numbers are currently distributed, it's really not possible to be better than that yet. The highest rated player is Magnus Carlsen, who's 2870 or something like that right now. He's flirted with 3,000, but he's never quite got there. The way that metric is computed is using an extension of this idea of z-scores. Essentially, you take an average value and you compare your performance to the average value to compute how you what your z-score would be in the entire distribution. And then when two players play against each other, essentially we can take the difference in their z-scores to decide a probability of winning for one player versus the other. And if the player that was expected to win wins, we can weight the result based on the probability of them winning. If they are significantly higher rated, then they were expected to win. So they can win, but they won't gain much in their rating points because that's what we expected to happen. On the other hand, if a person is, say, 400 points below and wins the match, then they were not expected to win, and they will go up a fair bit in rating by that win, and their opponent may go down a decent amount depending upon how many games they played and other things related to that. But it is built on this same idea of z-scores. It's called the ELO rating. And in fact, if you've ever looked at the website 538, they use a similar system to consider performance of sports teams. So you can see the ELO rating for all the NBA teams, how they're doing, what their predicted finish would be in the playoff race, and how particular games are expected to turn out. It's built on probabilities from those standardized z-scores. Kind of an interesting idea. All right. Well, then let's talk about the last major element from this unit. And this is called the empirical rule. And this is kind of halfway between what we talk about with descriptive statistics and what we talk about with probability. So bear with me. I'm going to describe the rule in words and then show you visually what it represents. So I actually have two rules I'll show you. The first is the empirical rule. And the empirical rule only applies to a distribution that is roughly bell-shaped. So think of it as unimodal and symmetric. If you've ever seen the normal curve or the bell curve, as they're often called, a distribution that looks roughly of that shape can have the empirical rule apply. When we standardize that kind of distribution using those z-scores, we actually find something neat happening between a z-value of -1 and +1, and between a z-value of -2 and +2, and -3 and +3. Each of those cases are telling us how many standard deviations on either side of the mean that we're looking. Okay? If it's symmetric and unimodal, it's going to be like the middle, a certain percentage, and then the next middle, a certain percentage, and so on. Well, here's how it works. Within one standard deviation of the mean, that means between one below and one above, we will find about 68% of all the values. So just more than 2/3 should be within one standard deviation of the mean. That's a lot. It's a lot of the data that happens to be right there. If we allow ourselves a little bit wider of a window between two standard deviations of the mean, so between two below and two above, we should find more values. And in fact, by the empirical rule, we find about 95% of all values are within two standard deviations of the mean. That's 19 out of every 20. If we widen yet further, within 3 standard deviations, we'll find about 99.7%. That is almost everything. And this idea actually will be what we can traffic on later to do hypothesis testing. We'll be using this same idea in slightly different contexts with some detailed checking to make sure that it applies, but it's the same basic ideas. It's the fact that if we know where our middle is, we expect almost all of the values to be within a certain range of that middle. Okay? And we can measure that using just the mean and the standard deviation and this empirical rule. Now, that's a lot of words and a lot of mathematics, so let's make sure we can see this visually. I drew in a standard, this is actually a normal distribution, but it's one example of the bell-shaped curve we're talking about. And so I labeled these key values. Suppose this is the mean in my entire population. And the standard deviation, I'm going to call it sigma. So mu plus sigma, that's one standard deviation above. Mu minus sigma is one standard deviation below. So that first line on the empirical rule said between one below and one above, this region right here in the middle, I should find 68% of all my data values. When we draw a curve like this, we usually do it so that the total area under the curve is 1, and that way the decimal we're looking at is equivalent to the percentage that it represents. So if this area here is 0.68, that would be 68% of all the area under that curve. Okay. Well, what if I widened this a little bit and I looked from 2 below to 2 above? Obviously, I should expect more than the 68%. The empirical rule tells me I can expect about 95%. 95% of the values will fall in those within that window, from 2 below to 2 above. What if I went even further and went as far as 3 standard deviations away? Again, there are still values that are above 3 standard deviations above the mean and below 3 standard deviations below the mean. There are still values in those two regions, those two tails. But most values, by and large, are here in the middle, between 3 below and 3 above. In fact, about 99.7% of all the values will be there. This is a remarkably useful fact, and again, we can use this to test hypotheses and actually draw conclusions simply from collecting a sufficiently large data set and comparing that to what we would expect under a null hypothesis. Okay, so that's the empirical rule. Okay. Key thing to remember, the empirical rule is always talking about the middle region. You need to know how many standard deviations away to decide which of these 3 values you're talking about. And second, it only applies when the underlying distribution is roughly bell-shaped. Okay, so unimodal has a peak right here at the middle and symmetric. So the left side and the right side look like basically the same. I almost always think of it as this shape because that's the most common context. But obviously it can look a little different. It can be steeper in the middle. It can be flatter in the middle. But it should be symmetric and unimodal and look roughly like this kind of a shape. Okay. Now, what if we wanted an equivalent to that, but we didn't have a unimodal symmetric bell-shaped distribution? Well, there's a mathematician who did a lot of things named Chebyshev. He actually did some work on prime numbers that is remarkable. But it was built on the same probability theory that he used to build his rule. It's called Chebyshev's rule. And it applies to this same context, but without requiring that bell shape in the distribution. So here's Chebyshev's rule. Unfortunately, Chebyshev's rule doesn't give us an exact value that falls within a certain region. What it gives us is a minimum value. We're guaranteed to find at least this percentage within a certain number of standard deviations of the mean. And the way it works, it actually works for any number of standard deviations. We can produce a specific formula. If I want to find within k standard deviations of the mean, I know I will find at least 1 minus 1 over k squared as a percentage of the values. Okay? Now to see how that plays out for different values of k, looking at that 1 standard deviation away, within 1 standard deviation, this tells me I would find at least 1 minus 1 over 1 squared. That's 1 minus 1. That's 0%. Well, that's not terribly helpful, right? I expect to find at least 0% within 1 standard deviation. Well, yeah, obviously. I can never find less than 0%. Okay. But within 2 standard deviations, I actually get some useful information. Within 2 standard deviations, I find at least 1 minus 1 over 2 squared, which is 1 minus a fourth. So I'll find at least 3/4 of the data. That's at least 75%. Okay? That's useful. Notice it's not quite as strong as what I had with the bell shape. With the bell shape, I had 68% within one standard deviation and 95% within 2. But within 3, I'm getting even further. 1 minus 1 over 3 squared is 1 minus a ninth. That's 8 ninths, which is about 88.8 repeating percent. It's closer to 88.9%, but since I'm using at least, I round it down. 88.8% is what I find here. And again, comparing that to the empirical rule, when I have that extra special shape, I get a little bit better. I get 99.7%. But here I have at least 88.8% regardless of the shape, which is, again, pretty remarkable. I don't need to know much at all about the shape. So I drew in an example here. I just tried to draw in a skewed distribution. This is actually an adjusted form of a log normal distribution, is what it's called. And this is not entirely precise, but this is close. Suppose this is where the mean happens to be. You can kind of see that it might be roughly there as a weighted average across all the different values. Okay. If this is my mean, and my standard deviation is such that this is 1 below and this is 2 below, I might have a skewed distribution where I have plenty of values that are well above the mean, and no values that are very far below the mean. But the concentration of values is here pretty close to it, right? Okay, so this is what this particular distribution looked like. I could draw this with others as well, and the nice thing about Chebyshev's rule is it applies everywhere. So